Okay, let's dive right into this explainer. We're looking at a massive industry-wide crisis that has honestly completely blindsided the automotive world. I mean, we're seeing a wave of catastrophic engine failures from historically extremely reliable brands. Our goal today is to uncover the real reason why this is happening all at once. And based on a deep dive into recent data and manufacturer documents, the source material reveals these aren't just isolated flukes, right? They're symptoms of a massive systemic shift in how modern engines are actually built.
Just to wrap our heads around the sheer scale of this problem, think about this for a second. General Motors recently had to recall 600,000 trucks because of catastrophic engine failure. 600,000! That isn't just a small batch of defective parts. We're talking about a massive chunk of their flagship fleet literally dying on the road. And you know what? It's definitely not just GM. The data shows that Honda currently has 1.4 million vehicles under federal investigation for similar issues. Toyota? They're navigating their second major engine recall in just 18 months. Meanwhile, Hyundai has already paid out over $1 billion in settlements for engines that failed, were replaced, and then somehow failed again. These are the four biggest names in the American market, and they're all experiencing the exact same implosion. So, what is actually going on here?
Section 1. Maximum power, minimum metal. So, the absolute crucial starting point is figuring out what physically changed under the hood. And the first factor starts with the immense stress engineers are now forced to put on significantly less metal.
The source material uses this brilliant analogy that I absolutely love. Think of the old 1990s 5.7-liter V8 like a 250-pound muscle guy. It made about 210 horsepower, had these massive, thick metal walls, and carried its load effortlessly. It was basically never pushed to its limit. But the modern 2.7-liter turbo? That's a 140-pound skinny kid. With turbochargers, it pushes out 400 horsepower and generates over 2,000 psi of cylinder pressure. That's pressure you used to only see in purpose-built race cars. It's literally the skinny kid carrying the exact same heavy load as the muscle guy every single day, with half the metal to support it. Now, to actually make that incredibly dense, high-pressure engine work, engineers had to shrink the tolerances, the gaps between moving parts like the crankshaft and bearings, to absolute microscopic levels. We are talking about gaps of less than 70 microns. To put that into perspective, a single human hair is about 70 microns thick. That leaves absolutely zero margin for error inside these modern engines.
Section 2, the thin oil problem. Let's see how this builds into an even larger issue, because the very lifeblood of your engine has actually been intentionally compromised to meet modern demands. You can see exactly how oil viscosity has evolved over time. 20 years ago, engines ran on a nice, thick, protective 5W30 oil. But because thinner oil creates less internal drag, the viscosity has been relentlessly dialed back to squeeze out slightly better fuel efficiency. We went from 5W30 down to 0W20, and now some of the newest engines are speccing 0W8 oil. Let me tell you, if you poured 0W8 on your hands right now, it would feel almost exactly like water. That incredibly thin film is literally the only thing standing between your engine's internal parts and total destruction.
And this thin oil becomes highly problematic when you consider what happened to engine bearings. Older bearings featured a soft lead overlay. If a microscopic piece of dirt got into the oil, that soft lead would just absorb it, safely embedding the debris away from the moving parts. It was like a sponge. But due to modern environmental regulations targeting toxic materials, that lead was completely removed. Manufacturers now use hard aluminum alloys instead. Are they cleaner for the environment? Yes, absolutely. But they have zero forgiveness. Any debris caught in that water-thin oil will instantly score and tear up these hard bearings.
Now, if you're wondering if manufacturers actually know this ultra-thin oil is an issue, well, GM's own recall remedy for their 6.2-liter V8s is pretty telling. To fix their engine failure issue, GM literally told dealerships to switch the oil from a 0W20 to a 0W40. They quite literally doubled the oil thickness. Dirt and manufacturing defects don't care how thick your oil is, which strongly suggests that the 0W20 oil originally specified was simply too thin to protect the engine out in the real world.
Section 3. Manufacturing chaos and debris. So what actually happens when you introduce microscopic dirt into an engine that relies on water-thin oil and zero forgiveness bearings? Well, the results are, quite frankly, explosive.
And listen, we aren't dealing with internet rumors here. According to federal NHTSA documents, giants like Toyota and GM have officially admitted, on paper, that microscopic razor-sharp machining debris was left inside their engines during the manufacturing process. Because the clearances are so incredibly tight and the oil is so thin, this metallic dust is basically acting like high-speed sandpaper, destroying the engines from the inside out before the vehicle ever even leaves the dealer lot.
The sources point out a very specific reason why we're seeing such a massive explosion in complaint volumes right now. Think back to the extreme manufacturing chaos between 2020 and 2022. Factories were running on skeleton crews. Unproven new suppliers had to be utilized because the established ones were completely shut down. Quality inspections were drastically reduced, and normal validation protocols were just bypassed. Stellantis even reported finding actual casting sand trapped inside engine blocks. Vehicles built during this incredibly chaotic window are just now hitting that 60,000 to 100,000 mile mark, which is exactly when those hidden factory defects finally rear their ugly heads and cause catastrophic failure.
Section 4. Start-stop abuse. As if the manufacturing debris and thin oil weren't bad enough, let's take a look at a common daily driving feature that is actively accelerating this bearing wear. A typical city commute might force your engine through 40 to 50 start-stop cycles in a single day. Every single time you stop at a red light and the engine shuts off, your oil pressure drops to absolute zero. When the light turns green and the engine fires back up, there's a fraction of a second where the bearings spin completely dry. With old, thick oil, a protective film would linger on the parts, but with modern water-thin oil, every single one of those 40 to 50 cycles is a brutal dry start, causing microscopic wear events over and over and over again.
Section 5. The ultimate root cause. So the really obvious question here is why on earth would brilliant engineers intentionally design engines with water-thin oil, ultra-tight tolerances, and highly stressful start-stop systems?
The analysis points directly to CAFE standards as the true culprit. This is an impartial government benchmark, the corporate average fuel economy rules that literally forces engineers to hit extremely strict average miles per gallon targets across their entire fleet. If they don't squeeze every possible fraction of fuel efficiency out of an engine by absolutely any means necessary, the financial penalties are massive.
It really all comes down to a single number: $17. Manufacturers are fined $17 per vehicle for every single tenth of a mile per gallon they fall short of their target. Let's just do the math on that for a second. If a manufacturer sells 2 million vehicles and misses their target by just 1 single mile per gallon, they get hit with a $300 million fine. No way around it. Faced with those kinds of astronomical numbers, the source material suggests that manufacturers simply ran the math and made a very calculated business decision. A predictable rate of engine failures, warranty claims, and lawsuit settlements simply costs less than paying billions in federal fuel economy fines. They didn't forget how to build reliable engines, folks. They just had to prioritize regulatory compliance over long-term, 200,000-mile reliability.
Section 6. Protect your vehicle today. Okay, you obviously can't change how your $80,000 truck was engineered at the factory, but let's dive into the highly actionable steps you can take right now to protect your investment. You can start stacking the odds in your favor immediately. First up, check NHTSA.gov right now to see if you have an open recall and get it fixed if you do. Second, cut your oil change intervals in half. If the manual says 7,500 miles, do it at 4,000 to continuously flush out any of that microscopic debris. Third, manually disable that start-stop button every single time you drive to save your bearings from those brutal dry starts. And finally, if your vehicle is out of warranty, strongly consider stepping up one oil grade, like moving from a 0W20 to a 5W30, just to give those internal parts a thicker fighting chance.
Oh, and if you're currently in the used car market, the data strongly suggests steering completely clear of the chaotic 2021 to 2024 production years. Paradoxically, you might actually be significantly safer buying a slightly older 2016 to 2019 naturally aspirated V8 with higher highway miles than a newer 2022 twin-turbo engine that's just been subjected to relentless city start-stop driving.
I want to leave you with this final, really important thought as we wrap up this explainer. As the automotive industry continues to push the absolute physical limits of engineering just to satisfy regulatory fuel targets, we really have to ask ourselves, are these marginal, fractional gains in fuel economy actually worth the devastating financial and environmental cost of a blown engine at 35,000 miles? It's a question every single driver and engineer is going to have to face in the years ahead.